Good morning. It's Tuesday. It's true. So my name is George. I'm the CEO of Comma.ai, and our slogan is Ghost Riding for the masses. What we have, this is a Comma Neo. This you can download off of our GitHub. You can download the plans for it, and you can build one of these yourself. It goes in your car, and we also have a dashcam app. It's a cloud-based dashcam app, and the cool thing about it is you can download it right now. It's available on both Google Play and the App Store. And so right now it's just a dashcam, but the dream, the soon-to-be plan, is to offer some ADAS features in the dashcam, right? So we'll offer some forward collision warning, some lane departure warning, good lane departure warning, not useless lane departure warning like most, I mean, seriously, most people turn it off. But if you want those kind of features today, if you build a Comma Neo, you can install OpenPilot. OpenPilot is our open source level 2 driving agent. And I'll say this now, it's better than Autopilot 2. I mean, it is. It's not better than Autopilot 8. Autopilot 8 was pretty good on the old hardware. It's about on par with Autopilot 7. Autopilot 2 is terrible. Autopilot's better. You can download this, and you can put this in your car. We have a couple of videos of it working. That's the GitHub URL for it. And it's open source. So if it doesn't work with your car, you can add support for your car. People have actually done this, and hopefully we'll be merging the changes upstream soon. But yeah, so I said level 2. What does that mean? Here are the official self-driving levels. I think that's SAE and that's NHTSA. Let's zoom in a little on the SAE one. The system takes over both steering and acceleration and deceleration in a defined use case. That's level 2. Level 4. The driver can hand over the entire driving task to the system in a defined use case. Wait a second. Steering, acceleration, deceleration. What am I missing? What's the difference? They say the same thing, right? Like steering, acceleration, deceleration, the entire driving task, that's the same. It's very confusing. Well, maybe, you got to employ people, so they got to make it confusing, right? But let's go through what self-driving levels actually are, right? So you have level 0. Everyone knows what level 0 is. No autonomy. You have level 1, cruise control, AEB, ACC, what you're seeing in a lot of the traditional auto manufacturers today. And then there's really 2 level 2 systems out there. There's Tesla Autopilot and there's Comma.ai OpenPilot. And we'll get to like a better definition of sort of what this means, but those things are capable of doing the steering, the acceleration, and the deceleration. So why are there more levels? Have you guys seen this before? Who's seen the levels for self-driving cars? Good, a lot of people have seen it, right? Why are there more? Well, the ones after 2 are liability levels, right? In 0 through 2, the automaker never takes liability. In 3, the automaker takes liability sometimes. And in 4, the automaker always takes liability. The only difference between level 2 and level 4 is insurance, right? Insurance is a real simple industry. Insurance is like reverse gambling, right? Where they're the house. They bet on things. They know they have their actuary tables, right? So if we build a system and we get it out there to a lot of people, and we can show that like on one stretch of highway, statistically, it's actually safer than humans, then we can sell that liability to an insurance company, right? And then for that stretch of highway, it's level 3, right? And then you do more and more and more, and eventually you get to level 4. How anybody thinks that there's going to be some magical jump to level 4 baffles me, right? You want to prove something's a good driver. Do it statistically. Get a system out there as quickly as you possibly can. Iterate on it. And this is the Tesla strategy, and this is also the Comma.ai strategy. If Tesla's the iOS of self-driving cars, we want to be the Android. But OK, so let's talk about the only number that actually matters, right? Forget all this level stuff. Let's just talk about disengagement events, right? So this is miles you can go between disengagements, like kind of like mean time between failure kind of stuff, right? I got a bunch of numbers. It's a vaguely logarithmic scale. Down here in 1, you have like the legacy automakers, right? If you get a Mercedes, a Ford, or a Honda, you get on the highway, you put on all of the self-assist features, you'll maybe go a mile between actually having to do something, right? Then you have a bunch of systems that are 10x better. It's kind of where we are. It's where Tesla is. Even Uber and Cruise fall around here. They're kind of doing different parts of the problem, but they still have a disengagement event about every 10 miles. This is where almost all the self-driving startups are right now. There's one company that's 100x better, and everyone should know what they are. right? The best technology by far. And then, what's at 100,000? Does anyone know? That's what people are, right? People crash about once every 100,000 miles. It's a rough number. But, and then you have some people who are thinking autonomous vehicles are going to get you here. This is impossible. You can write the world's most perfect autonomy software. What if a wheel falls off the car? Right? Like there's so many failures. Never is impossible. And it's absurd to try to talk about this. This is the level of risk that we are willing to tolerate. You know, 30,000 people die every year in car crashes in America, right? This is acceptable. If we could get a system that's better than this, that's it. That's victory, right? So let's talk about how to actually do that. I mean, you can see there's maybe an 100x gap between all the other players. OK, so you have the automakers down there. They're kind of hopeless. You see about a 100x gap between the startups and Google. And then you see another 100x gap between Google and the people. Yeah, so let's talk about what you'd actually have to do to close that gap. So our mission, this slide is a different color because it was in our pitch deck. It's been the same all along, to build the world's first superhuman self-driving agent. And I think from the last slide, we now have a rigorous definition of what superhuman means. Right? So build a superhuman driving agent. So let's talk about robotics, right? Let's talk a little bit about, it's kind of how I break down the self-driving car problem, right? You have localization, where am I? Perception, what's around me? Planning, what do I do? Controls, how do I do it? One of these 4 blocks is already solved. Controls is solved. You have a model for the car. Also, controls for like highway driving, it's so linear, right? It's such a simple problem. You're not trying to do some like fancy control system. This isn't helicopters doing inverted hovers. This is like, I turn the wheel a tiny bit, I step on the pedal a tiny bit, right? Smooth driving is safe driving. Let's talk about the other ones. Localization, where am I? Down to like centimeters accuracy. This is solved with money. You can do this today. You have like Google and Cruise. What they're doing, they're using a LiDAR. They have pre-mapped regions. And you can get really good localization if you throw money at the problem. Perception is tricky on the long tail. So remember, Google's been at this for 10 years. Google's probably the only company who you can kind of say has solved perception for self-driving cars. I think almost all their disengagements are not perception failures. They are planar failures. This is the hard problem. With the top 2, you can get to 1,000 miles between disengagements. I mean, obviously, you need some planning, but not like fancy, sophisticated planning. If you want to get to the 100,000 miles, you need everything on the board. So yeah, let's talk about localization and perception. Like I said, perception is solved by Google using a lot of debugging. Localization, could build it for you in 2 weeks if you give me a LiDAR and some maps. But how do you do it on commodity hardware? And what's really interesting about commodity hardware is Comma.ai. You can get this today, right? But what's the advantage? Like, you look at these fleets, right? These companies that have fleets. Google has a fleet. Cruise has a fleet. The automakers have fleets. Delphi has a fleet. They're tiny. We already have the world's 2nd largest fleet. Obviously, Tesla's the first, right? Doing this on commodity hardware enables you to actually ship this. If you build a Neo today and put this on your car, right now we're about 10 miles between disengagements, you're going to get all the way up to 1,000 just with software updates. You're going to see the exact same thing happen with Tesla, too. Camera only. Oh, you need LiDAR. LiDAR is the enabling technology for self-driving cars. I feel like a lot of auto manufacturers think that all you have to do is, well, we get a LiDAR, and we get HD maps, and then we have our integration engineers put the bolt between them, and that's how you solve self-driving cars, right? If you don't think camera only is possible, let's do a little thought experiment. 360 camera plus Oculus Man. He could drive the car, right? Does anyone really doubt that? Does anyone doubt that that guy could drive the car with the Oculus? And okay, so the link is very hard. Assuming you have some magical high bandwidth, low latency, no network service issues link, you drive the car no problem, right? And if that's possible, it's clearly just a software problem, right? The thing too about LiDAR is like a lot of what LiDAR helps you with is like maybe the first 5 layers in your ConvNet. You can do incredible things today with cameras, like segnets and depth nets. You know, this is from Comma coloring. You can see where the lane markings are, where the road is, where the cars are, where the traffic lights are, where the undrivable obstacles are. You have depth nets. You have mono depth nets. So you also don't need 2 cameras. 2 cameras is another one of these. Oh, you need 2 cameras. I think Bosch loves the 2 cameras. Oh, you don't need 2 cameras, right? So you can infer tons of depth information, even from just a static picture of a road, because you're in a constrained environment, right? Everyone kind of knows how big a car is. Also, we let people with 1 eye drive. To think that the 2 eyes are actually helping you with the driving problem at all is kind of absurd. Your baseline is about 7 inches as a human. I think that gives you resolution out to maybe 10 or 20 meters. Right? Most of the things you're doing when you're driving is way further away than 10 or 20 meters. Actually, people have no idea how far things actually are on the road or how long lane lines are. But yeah, so you have segnets and depth nets. And obviously, you don't just have to get depth in one picture. You can also use structure from motion techniques. Right? You can think about 1 camera moving as the same as 2 cameras. Here's a camera. Here's a camera. I have good odometry on my car. I know what the translation and rotation is between them. There you go. You got depth, right? So you can do incredible things with cameras today. So that's kind of the perception problem. Localization. This video is from our dash cam. The SLAM problem is much more constrained if you know that what you're in is a car, right? If you're trying to solve SLAM for like inside-out VR, right? You're like waving a phone around and you want to recover both the path and the objects. That's pretty hard, right? Especially when you start to deal with things like rolling shutter artifacts. But in a car, this is all easy because the movement is so defined, right? You think about the 6 degrees of freedom of arbitrary camera transformations. And in a car, I mean, that's kind of only 2, right? You got the this way, and the this way. Right? There's a little bit more to it, but mostly with those 2 dimensions, you can specify a lot of the stuff about the camera transform, and then your bundle adjustment does a phenomenal job kind of filling in the really small values for the other dimensions. So yeah, I mean, you want to build a centimeter accurate, or a 10 centimeter accurate localization system from a cell phone, gather pictures, write the code, slam the world. Yeah, I think we have let me see what the next slide is. Let's talk about the other problem. Right? So that's localization and perception. They're kind of solved with money. We'll solve them on commodity hardware. Now planning. There's only one system in the world that solved planning. That's people. AI hasn't solved this yet. Right? And there's kind of a few tricky problems. So you have a long time horizon learning, right? So if you have like an LSTM, you could do like backpropagation through time for maybe 50 steps. Beyond that, it gets kind of, I mean, even LSTMs, right? Maybe in RNN, you could go back 5 steps before your gradients explode or vanish. LSTMs, you could go back maybe 10x that. But 50 steps back, if you have a camera, our camera loop runs at 20 hertz. That's 2.5 seconds, right? That's not really long enough to have the kind of context you need. You need to kind of get another 10x from somewhere. There's the other problem, which is behavioral cloning doesn't really work to learn a task like this. What you really want to do is reinforcement learning. But in order to do reinforcement learning, you can't do this from fixed sets of data, right? So you need kind of 2 things. You need a simulator, which lets you deviate from what your data actually did, and you need a reward function, which, how do you specify that for driving, right? I mean, you could have this vague reward function of don't crash, but certainly in your data sets, crash events are very, very rare, and we're not going to let cars go out and actually explore on the roads, right? It's all about, you ship something, it better be all exploitation and not exploration. So you have like this thing called inverse reinforcement learning. The main paper that you hear about when you hear about inverse reinforcement learning is the Stanford helicopter paper. Really cool paper. But they're solving fundamentally a different problem from self-driving cars. The inverse, the helicopter, like getting a helicopter to do an inverted hover, it's really easy to specify, old school, when a helicopter is doing an inverted hover. It's just a question of what control inputs do I actually do to get it into that state and to get it into that state and stable, right? So there, inverse reinforcement learning works really well. But the car driving problem isn't this. It's actually really easy once you know what state you want to be in to figure out how to get there, right? Now, of course, you could say, OK, finally, the state I want to be in is parked outside of this Taco Bell. I mean, yeah, OK, backprop that through your 30-minute commute, it doesn't work, right? So you need something else to solve planning. And both of these things, you're starting to see the writing on the wall. So dilated causal convolutions from WaveNet. I mean, it's a cute trick. They kind of turn n into log n. And n into log n is, well, sort of what you need to get that 10x. This is WaveNet. They did audio synthesis stuff. And the convolutions are causal. The arrows all point forward through time because we make an assumption, and it's a pretty good assumption, that events in the future don't cause events of the past. So you kind of have the arrows all flowing this way. It's dilated, so you can get these really long time horizons. Yeah, so you can kind of see that dealing with the time horizon problem. The other problem is kind of dealt with by GANs, right? You can learn a world model. What's a world model? It's a function given the state at time t and the action at time t that gives you the state at time t plus 1. And you can even learn a reward function. And you can learn a reward function by kind of assuming that the average is good. I mean, not exactly the average. It's a little bit more sophisticated than that. You have to learn to reject other kinds of noise. It's clearly not just a beautiful Gaussian. But you can learn a reward function using these, probably using a GAN. We have a paper about this. It's kind of like, yeah, we learn a world model. The problem with learning the world model is, well, it works for about 2.5 seconds. So you need sort of both of these operating together to truly solve planning in a generic way, right? So you think about what's being done right now to try to solve planning. You look at Google and Uber, and they have this big, well, it's a hand-engineered feature space, right? They talk about three-dimensional bounding boxes for cars. They talk about three-dimensional bounding boxes for people. They talk about the state of the police officer's arm. You ever remember that in the Google TED video, right? Like you're weirdly defining this feature space. And this is hand-engineered feature spaces. And if we've learned anything from the history of AI, it's that hand-engineered feature spaces always lose. So how do we not? Think about this. Like, how many dimensions is the driving? How many dimensions is the state when you're driving? Like, I don't think it's thousands. I don't think it's tens. I think it's probably like hundreds, right? I think you could succinctly describe almost any driving scenario in like a 512-dimensional vector, right? So it's just the question of getting the right thing to take it down to that state for you. And then in that state vector is where you can do your RL. You look at things like the DeepMind paper with Atari, and it's cute. But when you look at how much data really went in to doing that, it's a huge, huge amount for a simple game like Atari. What you really need is to get into some abstract, hopefully more smooth and more Gaussian feature space, and then do your reinforcement learning over there. And this is almost exactly what GANs do, and it's pretty incredible. I think we're going to see huge advances in both of these this year. So yeah, Comma.ai is not a research lab. We're not trying to solve these problems. I'm waiting for someone else to solve them, right? What do? Well, we gather really big data. Because clearly for all of these things, perception, localization, and planning, big data helps. So we have almost 1 million miles of data. And you say, oh, that's nothing compared to Tesla's 100 million. Well, a few things about Tesla's 100 million. They don't have the videos back for that. From the Autopilot 2 hardware, they're getting the videos back. But from the Autopilot 1 hardware, they're not. And you can know they're not because hardware-wise, the camera is only connected to the Mobileye, and then the Mobileye is only connected over CAN bus. Right? So your CAN bus 1 megabit, the Mobileye doesn't have a video codec on board. You could maybe store a few frames in the Mobileye's memory and then pull them out. And you've seen this if you've seen people pull the crash data from Teslas, right? But they're not getting all the video back. We have video for all of this. This is probably the most diverse driving data set in the world, too, right? So you don't want data from the same geographic area. You don't want data from the same phone mounting. You don't want data from the same lens. You don't want data from the same sensor. You want all of these things to be like kind of marginalized, right? You should be invariant to all of these things, right? You should be invariant to the maybe even the exact placement of the thing, right? Because humans kind of are. That's actually interesting. If you drive on the right and you go to the UK and you try to drive on the left, it takes a little bit to learn. And then what's even scarier, I come back from London and I almost sideswiped a truck. I didn't realize. Like, I just didn't realize that I didn't unlearn. And I was way too far over in the lane. But you can learn this pretty fast. So sideways translations are maybe something that's a little bit harder to deal with. But small variants of rotation, different sensors, different distortion models. It shouldn't matter that much for a driving agent. It does matter if you want to do things like SLAM. Particularly, there's a new from the LSD SLAM guy. There's a new paper that came out that's it's like direct sparse odometry. He's using not just geometric models of cameras, but photometric models of cameras. And that stuff is superhuman. Like in some weird ways like that, computer vision is superhuman. If you want to know like how far something is away, I mean, like getting your features from a 16 megapixel camera over a few frames, you can do this to some superhuman level of accuracy, which is pretty cool. But yeah, get big data. Step 2, own the network. So with data, you can only kind of do the behavioral cloning kind of thing. There's no exploration. You want to actually take the models you've trained and try them. And not try them in a simulator. Chris Ermston gave me an awesome quote. Simulation is doomed to succeed, right? If you really want to deal with all the final edge cases of the world, you're never going to code them into a simulator. And people who think you are, it's kind of like, it's the same things that kind of plagued computer vision for a long time, right? Like, okay, maybe you're not specifying the, you're not specifying the vision code, but you're still specifying the graphics code. You're still not dealing with all of these weird anomalies. You're only sort of dealing with like, your feature space is whatever you're putting into your renderer, right? So you want to own the network too. And the really cool thing about owning the network is you deploy a model, you see where the disengagement events are. Right? This is all level 2. So people are driving these cars, people are paying attention. They disengage the system, you get the data back about that disengagement, and there you go. It's reinforcement learning where the users are the agent. It's a big reinforcement learning algorithm being run on the world, right? Your time per like epoch is kind of slow, right? So you ship out the model in the morning, you get a bunch of disengagement events in, you backprop them, and backprop them, get a new model, ship it out the next morning. Maybe we can even lower that model feedback time. You don't start wanting to do learning on the device. Learning on the device scares me because you don't ever know if you're going to learn something bad, right? So you need, in order to do this and in order to make this safe, you need good tests. You need good tests that test both static data and dynamic data. Simulators are good for testing. They're just kind of not good for training. If your thing doesn't work in a simulator, it won't work in reality probably. If your thing does work in a simulator, it might tell you something about whether it works in reality, but not that much. So yeah, own the data, own the network. So people like when I have calls to action. Said this about a TechCrunch talk, when you call to action. Download a dashcam. It's available in the Google Play Store and the App Store. It's called Schiffer. It's pretty awesome. We're going to be rolling out ADAS features to it as well. Yeah, download it. And also, we are hiring. Comma.ai, reports of our demise have been greatly exaggerated. We're here, and I think we're going to win. But don't take my word for it. Go build one. It's pretty cool. Yeah. Let's take questions.
No, we'll get it on video.
Same question I asked the NVIDIA guy. What do you do with the bad data? It looked like you were only keeping a fraction of the video.
So we keep all the video. There's kind of no such thing as bad data. So all good drivers, as the Yannick Karenina quote, I gave this to The Verge when I was testing Vegas. All good drivers are good in the same way. All bad drivers are bad in different ways. Our nets don't behave like the average driver. They behave like the committee driver. Imagine you had 100 people in a room voting 100 times per second on what action the car should take. Even if 20 of them are bad drivers, this doesn't matter. Even if 50 of them are bad drivers, how are they all going to be bad in the same way? The good really stands out. So there is almost no such thing as like bad driving data. Now, how do you filter out? If you mean by bad data, like people who turn the dash cam on when it's sitting on a desk, I mean, that's trivial to filter out, right? We have a model that just kind of says, is this driving? Does it look kind of like driving? I mean, you just use a GAN for that, right? It's easy.
Do you know how many Neos have been built and deployed?
Yes. More than 50, less than 100.
Any other questions? Oh, coming.
Hi, back to the data question. So the good data is automatically judged, or if somebody looks at them?
No one looks at the data. So our whole pipeline is automatic ground truthing. So you can do, the reason automatic ground truthing works and it works so well is there's so much redundancy kind of in the data, right? So say you build models that do prediction on single frame. So you build models, this is a simple thing like lanes, right? You build models that extract the lanes from single frames of data, right? You kind of know if the model is doing well or badly based on temporal continuity. Now, this isn't perfect. There are still failures which can happen. But fortunately, the failures of neural nets are usually not like these kind of failures. They're usually not like persistently wrong unless it's persistently wrong in the ground truth. So we do some amount of hand labeling. Our seg nets come from hand labeled data sets. Our depth nets are automatically ground truthed using a combination of stereo and LiDAR. Our model that we actually ship to the car is trained using those other models to assist in ground truth recovery. So if, if you have a segnet and you're running on an image, you know whether it's driving data or not, right? You expect to have some proportion of sky, some proportion of road in the right sort of places. You can clearly tell whether it's a desk or not, right? You can also do this by some amount of 3D map recovery, some amount of, like I said, the camera is generally confined to a 2 degree of freedom space. If it doesn't look like it's in a 2 degree of freedom space, it's not driving data. You also have tons of correlation between the sensors, right? Even things as bad as GPS speed work pretty well. If you actually have a connection to the car, you get even more sensors too. You get the speedometer, and you get the steering angle sensor, and you get, cars have separate, every car that has traction control has a sensor on all 4 wheels, and this is almost always accessible on the CAN bus.
Coming.
What are your plans to get the cost down so more people can buy the hardware?
Well, the cost is already pretty low. If you're thinking about putting this thing on a car, I'm not sure how many gains we would get by lowering the cost less than $1,000. Right? I'm not sure how many more people would build something and connect it to their car if the cost was, say, 100 instead of 1,000. But, I mean, if you put things together in this talk, right, how different is the Comma Neo from Schiffer? What if you could make an app drive a car? We still use the radar. We still use the radar for adaptive cruise control. We can do vision-only adaptive cruise control, but it's not as good. Actually, radar adaptive cruise control is kind of superhuman because radar gives you speed as first-order information, right? Like humans are not very good at estimating 100 meters out what the speed differential of a car is. Right? It's kind of hard to tell because you're using like temporal difference, and you're like, okay, did first frame was 100? Was the next frame, was it 99 or 101? You can't tell, right? So yeah, got to do that first, but you can do it.
So as we move from left to right and have more miles per disengagement events, I mean, is there a concern around handling that trade-off between when the machine is in charge and when the human needs to take back over charge?
So you're like the handoff problem? Yes. Yeah, I mean, there's some amount of concern, right? So what we do is we have a 6-minute timer. The concern really only happens if like the car is driving for hours without any intervention, and then the human needs to intervene suddenly. So we have a 6-minute timer. If the human hasn't interacted with the car in 6 minutes, basically, you know, the system stops accelerating, and it beeps, throws up all these warnings. This is the same thing Tesla's doing. My hope is this, right? So if you're building a level 2 system, yeah, you probably want to keep some kind of timer like that, right? Or at least some better estimate of the system confidence. My hope is that if you get enough of these level 2 systems out there, even with the 6-minute timeout, you can start to classify what all of your disengagement events are. And you can say, look, on these kinds of roads, there's not a disengagement. And that's how you become level 3. Now, you can't do this with a cell phone, you know. You're not going to start saying the cell phone can do any sort of level 3 stuff. You're going to need better hardware to do it, but the hardware certainly exists today. You look at like NVIDIA's Drive PX2, make sure that there's like an ASIL-D chip that can do some amount of safety critical stuff. Our safety model basically works like this. It works assuming that the human is paying attention, right? And 6-minute timeout, warning when it pops up, same as Tesla. To try our best to ensure that, right? And the truth is, like, if people don't pay attention, they probably don't pay attention when they're driving that much anyway. Then there's even more you need than that to actually make a system safe. You need to make sure that whenever the human wants to take control of the car back, it's very easy for them to do it. And not all systems do this, actually. So most systems will disengage when you hit the brake. Every cruise control system disengages when you hit the brake. We disengage also when you hit the gas, right? Because if a car is braking when you don't want it to, humans' first reaction is hit the gas, right? And I'm surprised. Tesla Autopilot doesn't do this, right? These systems let you hit the gas and stay engaged. Then the really scary one, and this is why we realized we needed a gas disengagement. And this actually happens. This happened on the stock Honda system. You step on the gas, and okay, the car wants to brake, and it sees that the human stepped on the gas. What do, right? There's kind of 2 things you can do. One thing is continue to step on the brake and hit both pedals at the same time. Not very good. But the second one's actually worse, which is if the human is hitting the gas, suspend the brake. So what actually ends up happening here is the human steps on the gas, the brake stops, they're like, oh, this is pretty nice. They let off the gas, the car still wants to brake, it hits the brake. That's how you get rear-ended, right? So this is why we disengage when you hit the gas. So disengagements are very intuitive. We don't disengage on steering, though. Some of these systems disengage on steering, and like our safety model for steering is this. Our system's incapable of putting more torque on the wheel. So it's 2 things that are dangerous on steering. This gets into like the second safety principle in general, which is always make sure the car doesn't do something, doesn't jerk, doesn't do something quicker than a human can respond. So in order to do this, you put actuation limits on stuff. And you can have like ramp up on some actuation. You know, don't come out ever with 1G of braking, but if you slowly ramp up to 1G of braking and the user doesn't do anything, that's probably the right choice, right? And you can, you know, gather data for all of this and try it. But yeah, for steering, we make sure that the amount of torque put on the steering wheel, it's only like the torque you could put on with like a pinky, right? So imagine someone was trying to push the steering wheel with a pinky while you had your hand on it. I mean, you'd kind of feel them pushing a little bit, but you know, it doesn't do anything. So yeah, the two safety principles are always make sure the user can take control intuitively and easily, and make sure that the car will never do anything so quick that the user doesn't have time to respond, assuming the user is paying attention. People do pay attention, right? I mean, you've seen this like, okay, there's the Tesla autopilot death, it's all over the news, but what about all the people who drove it and paid fine attention? And then what about all the people who didn't pay attention without Tesla autopilot and also crashed their cars, right? So yeah, I mean, at the end of the day, it's all about the numbers.
Question back here.
This is just a little bit of like a fanboyish question, but do you ever host like drive-in hackathons?
We
where
thought
could
about it,
drive in our
actually.
cars and work with people who know a lot more about building these things than we do to build our own?
We've thought about it. We've thought about kind of hosting like a Comma.ai hackathon kind of as like a recruiting thing. Yeah, maybe we'll think more about it.
Cool. One more question.
Considering the bad data that we talked about, I have to strongly disagree with you in one point. And I think there's a lot of situations where a lot of people drive bad in the same way. And it might even be because the human sensors are not good enough. For example, I could imagine invisible eyes that a human could not see, but the camera sees it. So all the humans, they don't slow down because they don't see it. And the camera or your whole system thinks, okay, there's eyes, but apparently that's not a reason to slow down because nobody did it. So in that case, I would definitely say that's bad data and we should somehow filter it out.
Well, okay, so you can do a few things. One, you can look at, you have the future. Having the future is a very, very powerful thing. You know what happened, right? So there is some amount of, regret that you can assign to something, right? So yeah, obviously if a human crashed, that's clearly bad data. You need a lot of data before you get a statistically significant amount of crash events. But I mean, that specific edge case, yeah, maybe you look for crashes, right? But the truth is, humans driving badly, if you define badly as like by the rules of the road, you don't want to drive by the rules of the road. You know how many times the Google car has been rear-ended? And you watch it drive around Mountain View and you see why. So everybody working on this understands that you need to make your car predict the world around you. You need to predict what's going to happen and what other people are going to do. But there's another component as well. You need to drive predictably. You need to drive in the way humans expect you to drive. Anyone who is talking about vehicle-to-vehicle communication, a future city where all the cars are these magical level 4, this is deluded. In reality, if you want to ship a self-driving car, you're going to be interoperating with humans for a long time. And in order to safely interoperate with humans, you don't just have to predict what they are going to do, you have to drive predictably yourself. When is a driver bad? You're on the road, you look around. Why is that car driving badly? Because you're driving unpredictably. Swerving in between lanes, turning without signaling. Right? These are obvious cases, but there's so much more to it, right? Driving is not some very rigid, specified problem. If it was, then I could write up a reward function. Driving is an intuitive dance between humans, and to solve it means kind of behaving like a human, and I think the solution that solves this will also be the solution for an untold number of robotics applications. I say this, I shouldn't say it anymore, but the real goal of Comma.ai is to end all jobs. Just kidding, chump, just kidding.